Right, that wasn't meant to happen. So I'm Joanna Leng. I'm at the University of Leeds currently with a EPSRC funded RSE fellowship. I don't really need to talk about that. It goes through this in the slides. So I'm looking at, I've been working in this area about 25 years. So we're looking at over that time how computers have changed science. I'm not looking at more general society, and a few predictions on how that will continue. I'm hoping that will help you sort of work out what your career paths are. And on the right, we've got some pictures from my fellowship where I'm looking at software for novel forms of imaging. So we've got diamond light source, a HPC system, Leeds Picture House. I thought that was a nice thing to have because I'm in Leeds. So we've got that. So this is my background. I did a degree in biophysics at Leeds. It was a 4-year degree. We had a strong elements of imaging and Fourier transforms. And then for a while, I worked in medical testing after that. Didn't like the salary, it was quite low. So I decided to do a conversion to computer science. And I did a project in medical visualization. The plan really was to go into outside academia, but I ended up staying there for various reasons. So this is some photos of my thesis. As you can see, it was a hardback edition, cost 80 quid to print, and I could only afford to have 2 colour images in it, which I think is very different from the sort of thesis that you publish today, which goes online and every image is colour.
So we're not seeing the same slide as you're looking at.
What slide are you seeing?
We're looking at slide 1 that's not in full screen.
All right, so
it was fine early on. Something happened.
Yeah, no, I know what happened. I think let's go for this is the one that's in. Can you see that now?
Yes, that's perfect.
Right, so we're out of sync with the text and the images now for your recording, but so this is the front page. This is my background, and you can see the images of my thesis here, which was hardback. I think I exaggerated slightly. I think it was about £70 to print. So you didn't want to have corrections because that was going to cost you money, and you had to put things in. But everything's colour now because it's all online, which is great. So from 1996 to 1999, I started working in an academic visualization service, which is where I'd done my project. And this is the desktop system that I had. I had a STI Onyx with a very large cathode ray tube visual display unit. The image size wasn't very big or great. I got it. I used Emacs for text editing. It used formatting to make the programming languages look better. And I was programming for graphics, so it's C, C++. And IRIX was the SDI's proprietary closed source version of Unix, which was what they had at the time. Everything I wrote was released to an open source repository that we held locally. And we had in the bookcase at the end of the room all the hard copy documentation printed in. And that was a bit like the water cooler of the time. You'd stand in a queue to look at the documentation and chat to people who were there while you looked at it. And so while I was there in the room opposite me, there were some guys rebuilding the Manchester Baby, which had happened 50 years before, which is twice the time since I started being a programmer. So you can see here, the memory was very, very small. And this is a picture of the program, an example program on the right. So this is very different. There was massive changes in that 50 years. I don't think the next 50 years are going to be quite so dramatic, but I think there'll be very many more, and across more of society and science. So as an outcome of the celebration of the Manchester Baby, I was given some research data from some archaeologists of an Egyptian mummy, and I managed to create some images and some videos showing the inside of the mummy. And this was the most important, the work that's been most prominent that I've done in all my time. and it was the first thing I did really. So that's quite amusing. SDI copied this sort of thing afterwards. They did a big project on an Egyptian mummy in London, and we've seen a lot more digitization, a lot more data coming from museums and archaeologists and all sorts of places since then. So one of the things that we looked at in visualization, when we developed visualization systems at this time, we looked at the how scientific exploration was done. And you can see that there is you have an insight, you generate a hypothesis, you explore that hypothesis with a set of experiments, and then you look at the results. And the visualization fits here as a post-processing part, but I think visualization is on every point on that model now. And that model is fundamentally changing because of AI and ML. So that was the old style. There are lots of different models of scientific investigation, but that's the basic one. And the other one we had, which was a view of a pipeline, the visualization pipeline. But over time, there's pipelines everywhere for different computations. And now there's a massive emphasis on workflows, which are very important. So this was one of the things, and you can make this into a distributed computing problem. Often you do that with the number of screens you're looking at it with. That's the most obvious place to put it up, where it goes to the graphics card. So, and then in 1999 to 2007, I joined an academic national HPC service. We used to put the word flagship in there. And we had a Cray T3E system, which had 576 CPU. And it was one system designed and developed with special networking to make it fast. That became more modular later, and we talk about that a little bit when we came into clusters. In fact, it was towards the end of this time that clusters happened. And at the time, we wouldn't have sent out newsletters digitally. We put them on our website, but we sent them out in the post, and there was a big thing every month. We put them in envelopes. And during this time, at the start of the service, we were run by SDI and who just bought out Cray. And then NVIDIA, because of the games market, recruited lots of SDI's hardware specialists. SDI then collapsed, and Cray was saved by the US government because Cray really is important to the US. And we went from Unix, which was built for each hardware system and proprietary and optimized for that system, and it became more modular. So then we got an open source Linux, and we found that with open source, bugs are fixed much more quickly because the community get into it and fix what's important to them. So I started working with virtual environments. We got a big screen system. I was the one person who did the visualization services for this national academic system. There wasn't direct funding for it, but I did it anyway. And here's some pictures of the sort of work we did. So on the left, you've got the virtual environments. So we had three HPC systems rendering for each part of that screen. We used a visual programming language to program the visualization things in, although you could dig into that and write your own software, which was what I was doing. And on the right, we've got some seismic tomography of the whole Earth. I think that we've got a universe in the middle, a tornado, and we've got an isosurface of porous rock at the bottom. So those are some of the things. It's only a small indicator of the sort of projects I worked on. So I took a year out from that project, and I worked on a project where we video streamed real-time interactive visualization footage down to a local operating theatre. When you've got rubber gloves on and there's lots of bodily fluids and blood on your hands, you need a special user interface. So we developed a special user interface and a GUI. This was under an NDA, so I can see some of the things that we did with the GUI have been more generally taken on by user interface people, but I'll not go into it. And I moved to Java for this, and I moved to Windows as well because the medics don't use Linux. And this was part of eScience. This is where we used to call it grid computing, but really that's now become cloud computing. And, you know, this VR is sort of the type of thing that metaverse Facebook is now taking on. But of course, that's not science. So I'm going slightly out of my remit with that one. But cloud computing is very definitely used for science these days. So I put this slide in because towards the end, I have less pictures. And this is just gratuitous pictures of my work with engineering, worked with geotechnical engineers quite a lot. We're using their finite element analysis codes. And right in front of us, this was put into the virtual environment. And it was there was a simulation of the CERN tunnel. They put a new elevator shaft in, and they didn't want to dislodge the circle. I can't remember what it's called, but where the route that the electrons and the atomic particles and subatomic particles go when you put the new elevator shaft in, they didn't want to damage that. So we have some various images on the right. We've got some images of soil displacing when you dig a hole. I think we've got a footbridge for a tunnel, for a bridge on the bottom, and on the right we've got some crack propagation simulations that I did visualizations for. So that's the sort of FEA work I did. And towards the end of this, you can see the very simplified views of things. This was the start of where images were used to generate meshes from image-based modeling or simulation, which I talk about partly later on and is part of my fellowship. So in 2007, it took 10 years to complete my part-time PhD, which was on a visualization toolkit for solar physicists. So I was doing what was considered a visualization case study work at that time. And 2 years into that study, the visualization community decided that they didn't like that research methodology, which caused me massive problems with my PhD. And I started to look at research methodologies, adoption of software, and how different scientific communities have interactions on each other at that time with the sociologists to look at that. So we have a series of images that sum up my PhD. On the left, I've got a simulation data set. I also had a sunspot data set. I put stochastic resonance in there, which was considered the way that sunspots were created from the day. And the pattern that I created out from that didn't match sunspots. So it looked like the theory that they had on how sunspots were produced, or the simulation, there were theoretical problems with that, which again is a sociological issue. And the visualization community at that time were thinking that this was more a user interface issue. They thought that bad user interfaces meant that software wasn't adopted. Whereas if you've got bad science in your software, it's not going to be adopted, was one of the main conclusions from my PhD. So then I had a career break, woohoo. And in 2013 to 2014, I came into biomechanical engineering for a short period. I didn't work with image-based simulation, but everybody in the office was. And you can see I'd worked with Simpleware very minorly in when I was worked on CSAR, and you can see here the complexity of the ribs and all the other organs. That would be very difficult to produce any other way without analysing images. And so you can simulate much more realistic systems with image-based modelling. And we had to have the right computers in the place before that became worthwhile. So from 2015 to 2018, I went into Leeds centralised HPC User Support group. By this time, computers have become much more modular. We had clusters, which is a modular way of building a computer. And instead of having the proprietary and vendor-specific hard networking, we had high-speed interconnects, which we bought with it. And you could you can pull out with these sorts of computers, you can pull out hard drives and CPU and nodes and change them on the fly while the computer's running. So they've become much more modular and fault tolerant. And during this time, the SSI was started up, and it started to sort of look at research software and quality issues in that. And they started to campaign for research software engineers, which is mainly focused on RSEs working in centralized teams. But at the same time, alongside that, open data has become ever more popular to match the data deluge. We have open data repositories. I use Zenodo. But this has led to concerns on reproducibility and open science. So this is a big area that's pushing the research methods to be looked at more carefully in the computational area. Yeah. So while I was in the centralized group, I was applying for this fellowship. So I worked out several strategies, and this is one of the strategies that I looked at. So this is a well-known representation or model of innovation in computing technologies. So on the left, you have a fluid phase where you need lots of flexibility, and on the right, you have stable products or services. And when you look at it this way, this on the right is where the RSEs in centralized teams, this is the sort of thing they tend to do. And most of the RSE fellows are in that area as well. But I really, really like the sort of innovation, the new flexible stuff. So that's where I placed myself. And that's also where a lot of the academic software developers are, where it's quite difficult to develop the software. But there's a gap there, and it's a problem. So it's a growth area in my opinion, that. So from 2018, I showed you what my desktop environment looked like at the beginning of my career, and this is what it looks like now. I have GPUs, they're used as accelerators. So accelerators are very common to tag on to any sort of computer, whether it's desktop or supercomputer. And I have two very big LED screens, so I can program on one side and see the results of the program on the other. I use a variety of visual programming things. Notepad++ is probably the closest to Emacs, but I use Visual Studio and Spider. And I also have them, I also can use Windows subsystem for Linux on my desktop, so that I can work with Linux software and C++. So virtualization has become more important. I use Anaconda Python, and I have version control, which I run from the command line, but I use linting within the programming environment. And occasionally, if there's a memory leak, I'll look at Valgrind to look at the memory leaks. I'm using Bitbucket and GitHub for repositories and trying to produce my software that's Python as PyPy modules, and I'm using Zenodo. And I've submitted something to JOS, which is the Journal for Open Source Software. So we can now publish software. Also, I don't have to queue up at the bookcase to look at the documentation, which is a shame because I can't chat to my mates and find out information sometimes a little bit more quickly than if I looked it up online. And all of my work for the last 2 years has been on Teams or Zoom. So computers have changed all of that. So the other thing with my fellowship, I chose to pick multiple partners for multiple projects because I thought that would spread the risk. So here's two of the projects quickly. I worked with Michelle Peckham and Alistair Curd on a type of high resolution light microscopy. We were looking at patterns that proteins form in there. And you can see there's some pictures on the right hand side of that. And then I also worked with, or have been working with, Rick Bridson and Nicole Hondo. And we're looking at each data point has a spectra of associated with it. The spectra, you know, when you were at school and you used to put things in the Bunsen burner and you used to get a coloured flame off it, it's the spectra for the colour flame effectively. And from that you can tell out what chemical species you've got in each point in the image. So here are two images of iron slag, and we can see there's some sort of structure inside, and there's a little video here of that as well. So I'm just working on that. It's not gone quite as fast as I would have liked. Oh, and I can't change screen. So, but the main work that I've been doing is with Sven Schroeder. He's in the School of Chemical and Process Engineering, and he needs software. He does a lot of work with Diamond Light Source, which is a big synchrotron down in Oxfordshire. And he has plenty of support and software help while he's at Diamond, but he doesn't have that on campus, which I think is common. And he really, really wants that sort of support and software to come into faculty. And with some of the work we've done on crystallization, we've got an exciting paper coming on, because it sort of looks at crystallization and hints that shows that there are other things going on there. So I can't see you, but can you spot the crystal in the middle of the screen? So they had hundreds and thousands of frames of video, and there was only the PhD student had to look through it and find video exactly where the crystals were, and where you'd expect it, the crystals in the middle of the screen. But it's very, very difficult to see, and you're not going to get any automated systems really to do much with that. So I found the Euler's video magnifier, and on the right you can see where that's applied, and that's still too faint to really do anything automated with the images. But we could also see other effects which are called non-equilibrium growth oiling out, which puts impurities in your crystals, which is if you're trying to make crystals to package medical tablets, then that's a problem. So here's a view of the crystal growth tracker software that we developed that will allow them to automatically trace this. It took the PhD student about 1.5 years to annotate the software once we got the Euler's magnifier in place without this software. So it's very painful doing that. There isn't really good software to do that. So this software and that research project are continuing. We've got a part-funded PhD student with AstraZeneca, and we're looking to use population balance modelling to see how good the experimental observational data is, and check that we understand how crystals grow. So of course, when you've got funding for a fellowship, you can expand your network, which hopefully brings you more funding in. So that's the aim. If you get funding, find more projects and more people to work with. So I've also been working with Sarah Harris and the FFEA team. They use cryo-EM data, and we have to mesh that to do some image-based modelling, which is mainly what the FFEA software does. And we're working on the meshing there. I also did a small amount of work with some doctors at the LGI, which is a literature review of how AI and ML can be used in certain spine issues around the shoulder, and how mobility of the shoulder can be affected in people with spinal damage or old age. So it's great working. I moved to the School of Computer Science for my fellowship, and all of a sudden I can supervise students, and that means I can test and have innovative ideas and work with great people who want to do new stuff. So we've got the meshing work going on with the FFEA group. We've got the PhD student with AstraZeneca, another one with Michelle Peckham and Alice. I'm also doing something with natural language processing, and I can see I've put the letters in the wrong order there. But I've also got some other students. In particular, I liked Paulina, who came to me. Both of the final year graduate students came to me, and we did computing, tech and society, living by algorithms. We did some experiments with Facebooks to work out what their biases were. So that's all quite good, and it allows you to do the more flexible stuff near the point of innovation. So now here, as I promised, here are some predictions of where I think the future's going to go. I think there's going to be more automation, particularly in Git services, and probably that means GitHub is going to lead that because they're owned by Microsoft, and they're doing that in part to reduce their cybersecurity research. So they're wanting to have much more secure software come out of that. But this will really affect new software. It won't help us deal and understand legacy code. So I'm not quite sure what's going to happen with legacy code. But as more automation comes in place, and as the computing becomes a more stable area, my prediction is that the people skills of software development is going to become more important than it currently is. We're still going to have more and more data from more and more sources, and there will be new computing technologies. I can't predict what they are, but we've got the Internet of Things, we've got the cloud, we've got all sorts of new things coming through, and that's going to create new areas of research, new research paradigms. So there's going to be a lot of discussion between the disciplines of how you accredit different types of disciplines. There'll be continued modularization of software, hardware and environments, and that's virtualization and containers. And that means you can develop workflows that use multiple bits of hardware and operating systems. And that could all be on one computer or multiple computers. So that's really moving in a very flexible way. And the silicon architecture for computers is definitely becoming more stable. The cycle of how quickly we need to change everything is slowing down. It used to be 2 or 3 years. I think our IT services has it as over 5 years now. So is that as the hardware lasts longer, then cloud becomes more economic, and then the pay-as-you-go model works more easily if the software is available through the cloud. So general purpose HPC, which is what the current N8 system is, and the HPC at the University of Leeds, is going to become less favourable. It will be developed specific HPC for specific types of problems. So systems with a lot of GPUs on, for example, are very good for AI and ML. And you can see that with the tier 2 systems currently. There are some very specific for AI and ML. And there will be other, well, there already are. That's a growing trend for about 10 years. There's a really big company in New York who've got a special system for drug discovery. And there are other ones for developing submarines. Of course, when you've got distributed computing and networking, that means that the network might drop out. So there's going to be looking at ways to recover and fault tolerance on remote systems. Remote working, learning and technical sharing is going to become even more popular. And both cloud and remote working will make computing more sustainable. It's more easy to recycle the components, and you've got issues with scale for the energy production and consumption, which will make that easier. So I suspect with global warming, that might become more popular. Quantum doesn't currently have a nice high-level programming language, but when that happens, I think quantum will take off. And quantum's really broken our encryption and cybersecurity. So we're going to have new paradigms around that, which will sort it out. I mean, at Leeds, we've had a lot of problems with cybersecurity. And I think if we can sort that out, we can work a lot more easily with computers in many ways. I think that'll take a while to happen. And this is more looking at the adoption of the computational method. So the SSI has really developed its campaign around moving RSEs into centralised teams, which are kind of outside academia. So I see them being national facilities, but we will lose that sort of flexibility on the innovation, which is the area I like to work in. That will be problematic. Eventually that'll have to be resolved. Currently, IT services best practices were developed outside universities and away from research environments where a lot of flexibility is needed. That's starting to be recognised. And new IT services practices will have to be developed and set up for research environments. Activities that are now considered IT services, maybe application support, networking for high throughput experimental systems, these are going to become recognised as important to research. In the 1990s, there was less demarcation in the area. So it was quite naturally done and shared, but we didn't have to think about whether it was research or not, and now we do. So I think that's going to be incorporated in. New research methods with AI, ML and all new computing technologies are going to have to be worked out and accepted for all the different areas of research where we use computers. Yeah, software and other outputs from research will become better accepted. Publications, I still think, will be the golden thing to create in academia, but I think they'll become more open. I very strongly suspect version control will start to be used. With open science, it makes it much more open, so I think we'll have named reviewers. And in the medical field, they're talking about when you get funding that you pre-agree, or the idea is that you could pre-agree what publications you would produce. And then if there are issues or problems with the research, you can publish them and you can present negative results. So at the moment, it's very difficult to present negative results, and that creates a bias in science. And finally, all of this means that there's going to have to be organisational structures and policies and practices that change in academia and in the funding bodies. So those are my predictions. I've got a lot of predictions there. I hope you kind of agree. Well, you're happy for you not to. And so thank you for listening. And what changes do you think will happen in your career? That's probably 30, 40 years. So that's there was a big difference at that beginning. Will it be as exciting? What do you think will happen? What trends will stop and which will start? So I'm ready for questions now.